December 1941, and America just got dragged into the largest war in human history. The Army needs tanks, thousands of them, and they need them yesterday. But there's a problem so massive it almost cost us the war before we even showed up to fight. The M4 Sherman, the tank that would eventually become the backbone of Allied armored forces, took over 300 hours to build. Let me put that in perspective for you. 300 hours means that if you started building a Sherman on Monday morning, you wouldn't finish it until 2 weeks later. The Germans were churning out Panzer IVs. The Japanese had already overrun half of Asia, and America's best tank factories were producing maybe 5 Shermans per week. 5 tanks per week. Do the math on that, and you'll realize we'd lose the war before 1943 even rolled around. The Roosevelt administration knew they had a nightmare on their hands. In early 1942, the president demanded 45,000 tanks by the end of 1943. Military planners looked at that number and quietly panicked. At the current production rate of 300+ hours per tank, hitting that target would require basically converting the entire American manufacturing base into nothing but tank factories. We're talking about a nation that just months earlier was still producing civilian cars and refrigerators. The infrastructure wasn't there. The skilled welders weren't there. The specialized machinery wasn't there. But here's where the story gets interesting, and why we're even talking about this 70-some years later. A handful of automotive executives and production engineers looked at that 300-hour assembly time and asked a question that would change military manufacturing forever. What if we're building tanks wrong? Not wrong in terms of design. The Sherman's layout was actually pretty solid, but wrong in terms of process. See, tanks in 1941 were still being built like they were in World War I. Craftsmen would essentially hand-build each vehicle, custom fitting plates, drilling holes on site, grinding welds to perfection. Every Sherman was slightly unique, which sounds romantic until you realize it's a logistics apocalypse. The guy who really saw the future was William Knudsen, a Danish immigrant who'd climbed from factory floor to president of General Motors. Roosevelt appointed him to head military production, and Knudsen brought something the Army had never seen before, the Detroit perspective. He'd spent decades perfecting automobile assembly lines where a Model T rolled off every 24 seconds. Knudsen looked at tank production and saw the same problems Ford had faced in 1910. Too much craft, not enough system. He pulled in executives from Chrysler, Fisher Body, and Ford, sat them down with Army ordnance officers and basically said, "Forget everything you know about building tanks. How would you build 50,000 cars?" That question, that fundamental reframing kicked off one of the most dramatic engineering transformations in history. By late 1943, Sherman production time had been slashed to under 10 hours in some facilities, not 300 hours, 10. That's a 97% reduction in assembly time, and it happened in less than 2 years. The breakthrough didn't come from the Army. It came from Fisher Body, a GM division that normally made car frames and shells. In early 1942, Fisher's engineers got their hands on the Sherman blueprints and immediately saw the problem. The tank was designed as one continuous welded structure. The hull alone required over 5,000 individual welds, most of them done in sequence because you couldn't reach certain joints until other sections were complete. Welders were literally climbing inside partially built hulls with torches, spending hours in cramped positions to join plates at awkward angles. It was slow. It required master craftsmen, and it created a massive bottleneck. Fisher's team, led by production chief John Alder, proposed something radical. Break the Sherman into 5 completely separate sub-assemblies that could be built simultaneously in different parts of the factory. The hull would split into a floor section, 2 side assemblies, a front Colossus plate unit, and a rear engine deck. Each sub-assembly would be built on its own dedicated line with specialized jigs, metal frameworks that held plates in perfect position. Instead of welders eyeballing measurements and hand-fitting pieces, the jigs guaranteed that every hull floor built in Detroit would be identical to every hull floor built in Chicago down to the millimeter. This modular approach did something extraordinary to the weld count. By designing sub-assemblies with flanges and bolt holes built in, Fisher reduced hole welds from over 5,000 to roughly 2,000. The remaining joins happened at final assembly, where cranes would lower the side sections onto the floor. Technicians would bolt them temporarily, and then a small team of welders would run continuous seams along pre-marked lines. What used to take 3 master welders 2 full days could now be done by 6 semi-skilled workers in 8 hours, because the jigs did the precision work. The Army initially fought this idea. Ordnance officers argued that bolted connections would be weaker than continuous welds, that battlefield damage to one subassembly would require replacing entire sections. But Pfizer ran stress tests at the Aberdeen Proving Ground in Maryland during spring 1942, and the data was undeniable. Modular Shermans could take the same punishment as traditionally built tanks. In one test, they fired a 75mm armor-piercing round at the joint between a side panel and floor section. The connection held, and the bolt pattern actually distributed impact stress better than a single weld line. By June 1942, Pfizer Body's modular method became the standard. The company published a 400-page manual titled Simplified Tank Assembly Procedures that got distributed to every Sherman contractor. Page 47 showed the sub-assembly breakdown with actual time savings. Hull floor 18 hours down to 6. Side panels 24 hours down to 8. Turret basket 16 hours down to 4. When you add it all up across every component, the modular redesign alone cut 120 hours off the production cycle before a single process improvement hit the factory floor. What Fisher Body did was essentially invent flat-pack furniture 60 years before IKEA made it mainstream. They proved you could take something as complex as a 30-ton armored vehicle and treat it like a collection of standardized parts that unskilled workers could assemble by following numbered steps. Now let's talk about the place where this modular system got put to the ultimate test, the Chrysler tank arsenal in Warren, Michigan. This wasn't some converted car factory. This was a purpose-built tank manufacturing fortress that broke ground in September 1940. A full year before Pearl Harbor. The government knew war was coming, and they handed Chrysler a blank check to design the most advanced armored vehicle production facility on Earth. When the doors opened in April 1941, the main assembly hall stretched $200 FT long. That's 4 football fields with overhead cranes capable of lifting entire Sherman hulls like they were toy blocks. The genius of Chrysler's setup was the conveyor system. They'd taken inspiration from Ford's River Rouge plant, but scaled it to tank dimensions. Picture a moving assembly line 40 FT wide, crawling forward at precisely 3.5 FT per minute. A bare hull frame would start at Station 1 on the north end, and as it rolled south through 113 designated workstations, teams would add components in carefully choreographed sequence. Suspension bogies at Station 12, transmission at Station 28, engine drop at Station 45, a 500 horsepower radial that weighed as much as a Volkswagen Beetle lowered by crane in 4 minutes flat. By the time that hull reached Station 113 at the south end, it was a complete running Sherman ready for the test track. But here's what made Chrysler truly revolutionary. Parallel sub-assembly lines feeding the main conveyor. While hulls moved down the center, 26 separate sidelines were building turrets, final drives, track assemblies, electrical harnesses, and gun mounts. Everything converged with split-second timing. A hull arriving at Station 67 would pause for exactly 18 minutes, while a completed turret built on Line 7B starting 2 hours earlier got lifted by crane and set onto the turret ring. The coordination required was insane. If Line 7B fell behind by even 30 minutes, the entire main line would have gaps. And gaps meant wasted capacity. The facility employed 10,000 workers at peak production, organized into 3 8-hour shifts that ran around the clock. By mid-1942, Chrysler had refined their process to the point where they were completing 1 Sherman every 8 hours. Not starting 1 every 8 hours, finishing 1. That's 3 tanks per day, 21 per week, roughly 90 per month from a single facility. For context, Germany's entire tank production across all factories in 1942 averaged about 500 vehicles monthly. Chrysler alone was producing nearly 20% of Germany's total output. The speed came with a cost, though. Quality control became an obsession. Chrysler instituted 47 inspection points along the main line. Each Sherman got driven through a water testing booth at Station 98, where high-pressure hoses blasted every seam to check for leaks. Turrets were rotated, 50 complete revolutions to verify bearing tolerances. Every gun breach was drift-fired 20 times. Vehicles that failed any inspection got shunted to our work bay, but the rejection rate by late 1943 was under 2%, which is remarkable for a factory hiring thousands of workers with zero manufacturing experience. While Chrysler was perfecting the main assembly line, Ford Motor Company was solving a completely different puzzle. How do you produce complex turret components without skilled machinists? Ford's Highland Park plant in Detroit had been building Model Ts since 1910, but turrets were a different beast. These weren't simple stamped metal shells. Sherman turrets required precision gun mounts with recoil mechanisms, elevation gears cut to tolerances of 0.02 in, and cast armor sections that had to be machined to exact specifications so the turret ring would rotate smoothly under combat stress. Traditional machining required craftsmen who'd spent years learning their trade. You couldn't just hand someone a turret casting and say, "Make this fit." Except Ford had already solved this exact problem in a different context. The B-24 Liberator bomber program at Willow Run. That facility, which opened in 1942, was producing 4-engine heavy bombers using workers who'd never seen an aircraft before. The secret was jigs and templates. So many specialized fixtures that workers didn't need to think. They just needed to follow color-coded instructions. Ford transferred this system to Sherman turret production with obsessive precision. Take the gun mount machining process, originally an 18-hour job for a master machinist. Ford broke it into 23 separate operations, each with its own dedicated machine tool and custom fixture. Station A would drill the primary bearing holes using a template that guaranteed perfect alignment. The casting would move to Station B, where another fixture guided the cutting tool for the recoil cylinder seat. Station channeled the elevation gear teeth. By Station W, that turret casting had been touched by 23 different workers, none of whom understood the complete assembly, but each of whom could perform their single task in under 15 minutes after a week of training. This is where Ford's time savings get almost unbelievable. The complete turret machining process from raw casting to ready for assembly component dropped from 18 hours to 90 minutes by August 1942. That's a 92% reduction. Ford published their methods in a technical report that October, and within 3 months every Sherman contractor had adopted similar jig systems. The Fisher Tank Arsenal in Grand Blanc, Michigan cut turret time to 85 minutes. The Pressed Steel Car Company in Pennsylvania hit 95 minutes. Even smaller contractors like the Pacific Car and Foundry in Seattle were below 2 hours by early 1943. The jig system had another massive advantage. It eliminated cumulative error. When a machinist hand measures and cuts, small inaccuracies add up. Maybe the first hole is 0.01 in off. The second is 0.0055 JoJo 15 and off in a different direction, and by the time you're done nothing quite fits. But jigs reset the accuracy with every operation. Each fixture referenced the original casting dimensions, so errors never compounded. This meant Ford could hire workers straight off the street. Literally, they ran recruitment drives in downtown Detroit offering $125 per hour and have them producing combat-ready turret components within 9 days of training. The Army tested turrets from all contractors at Aberdeen in October 1942, firing 500 rounds through each to check for mechanical failure. Pass rate 99.4%. These weren't inferior products made by unskilled labor. They were superior products made by superior systems. Here's where the whole operation could have collapsed. Imagine 7 different factories across America, each building Sherman components using different suppliers, different machine tools, and different raw materials. You'd end up with 7 different versions of the same tank. A turret built in Michigan wouldn't fit a hull from California. Tracks from one factory wouldn't match the drive sprockets from another. The Army would receive thousands of partially compatible vehicles that required custom fitting at depots before they could be shipped overseas. This is exactly what happened with British tank production early in the war. Different manufacturers produced Matildas and Crusaders with such variation that field mechanics needed factory representatives present just to swap major components. The Americans decided this was unacceptable, and they solved it with something called interchangeable parts at industrial scale. Now you might think interchangeable parts, that's not new. Eli Whitney invented that in 1800. True, but Whitney was making muskets with maybe 40 components. A Sherman had over 8,000 distinct parts. Getting all of those parts to be truly interchangeable across multiple factories built by different contractors required a level of standardization that had never been attempted. The War Production Board established the Tank Standardization Committee in February 1942. And they did something brilliant. They created master gauges. These weren't blueprints or technical drawings. They were actual physical objects, precision ground metal templates that defined exactly what a correct part looked like. Every contractor received a set of 340 master gauges for critical Sherman components. The turret ring gauge, for example, was a machined steel circle ground to a tolerance of plus or minus 0.05 in. If your turret ring matched that gauge, it would fit any Sherman hull in existence. If it didn't match, you scrapped it and started over. Factories implemented go-no-go inspection systems at every stage. A go gauge would slide into or over a correctly sized part. A no-go gauge, slightly larger or smaller, would not fit a correct part but would fit an out-of-spec part. Workers didn't need to read micrometers or understand tolerances. They just needed to check that the go gauge worked and the no-go gauge didn't. This binary system was foolproof. Fisher body inspectors in Grand Blanc would check 50 random transmission housings per shift, using the same gauges as Chrysler inspectors in Warren. If both factories' parts passed their respective gauges, those parts were guaranteed compatible. The proof came in the field. In November 1943, a Sherman from the Chrysler tank arsenal threw a track in North Africa. The replacement final drive came from Pfizer-Bod's Grand Blanc plant. The track sections came from Ford, and the bogie wheels came from Federal Machine and Welder in Ohio. The repair crew bolted everything together in 40 minutes without modification. Not a single hole needed to be re-drilled. Not a single bracket needed to be bent. Everything fit on the first try because 7 factories $2,000 Maya part were all building to the same exacting standards. By mid-1943, the interchangeability was so reliable that the Army stopped tracking which factory built which Sherman. They just ordered M4A1 medium tank and accepted delivery from whoever had capacity. Ordnance depots in England would stock spare parts from mixed sources, and mechanics never even asked where a component originated. Now we need to talk about the human side of this miracle, because all the jigs and gauges in the world don't matter if you can't find people to use them. In 1940, America had maybe 50,000 skilled welders, machinists, and metal fabricators, craftsmen who'd spent years learning their trade. The Sherman program alone needed 200,000 workers. And that's before you count aircraft, ships, artillery, and every other weapon system. The math didn't work. That traditional approach, apprenticeships, trade schools, years of training, would take until 1950 to build the workforce we needed in 1942. So, industry did something that sounds insane on paper. They broke master craftsmanship into microtasks so simple that literally anyone could learn them in days. This concept called labor dilution became the secret weapon of American production. Take hull welding. Traditionally, a job requiring 2 years of training to master, a skilled welder needed to understand metallurgy, recognize different steel grades by spark pattern, adjust torch temperature on the fly, and execute dozens of different weld types depending on joint geometry and load requirements. Chrysler's training department, led by a guy named Charles Sorensen, who'd learned manufacturing under Henry Ford himself, analyzed hull welding and discovered it consisted of exactly 47 distinct operations. Most of those operations were actually identical, running a bead along a straight vertical seam between 2 plates held in a jig. Only 7 operations required any real complexity like welding curved sections or overhead joints. So Sorensen split the job. 40 operations became Class B welder tasks that required 9 days of training. The 7 complex operations became Class A welder tasks, handled by experienced craftsmen, who were now freed up to focus on the genuinely difficult work. The training was incredibly specific. Class B welders at Chrysler didn't learn welding. They learned vertical fillet weld, 3 to 8 inch mild steel plate, 90 to joint stationary position. That's it. That's the entire job. They practiced that one weld type for 8 hours a day for 9 days straight, running thousands of practice beads on scrap steel until muscle memory took over. On day 10, they went to the production floor and ran that exact same weld on actual Sherman hulls. Nothing else. If a different weld type was needed, a different worker handled it. This system unlocked an entirely new labor pool. By late 1942, roughly 40% of Sherman production workers were women, many of them housewives with zero industrial experience. The Rosie the Riveter image is famous, but the reality was even more impressive. These weren't just propaganda figures. They were genuinely skilled operators performing complex manufacturing tasks. A woman named Rose Monroe worked at the Ford Willow Run plant installing turret bearings, a job requiring precision measurement to 0.201 in. She'd been a waitress 6 months earlier. Ford's records show her rejection rate was actually lower than the male workers she replaced, because she followed the checklist procedure exactly without trying to improvise. Thieves' range was equally wild. Chrysler hired 16-year-old boys straight out of high school for track assembly work. United Motors hired men in their 60s and 70s for gauge inspection roles that required good eyesight, but not physical strength. By 1943, the average Sherman worker had 11 months of manufacturing experience total, 11 months, and they were producing vehicles that could survive tank battles in the Ardennes forest. Building Shermans in 10 hours sounds impressive until you realize each tank required 18 tons of raw material that had to arrive at the factory at precisely the right moment. Too early and you're paying to store mountains of steel, copper, and rubber that tie up capital and warehouse space. Too late and your entire assembly line stops while 10,000 workers stand around waiting for parts. This is where the War Production Board faced a logistics challenge that made D-Day planning look simple. Coordinating the delivery of hundreds of different materials to 7 major tank factories without choking America's already overloaded railroad system. Let's break down what one Sherman actually consumed. The hull alone needed 15 tons of rolled armor plate in 4 different thicknesses. 2 in for the glasses, 1.5 in for sides, 1 in for the rear, and 0.5 in for the floor. That armor came from exactly 3 American steel mills capable of the specialized rolling process: Bethlehem Steel in Pennsylvania, Carnegie Steel in Ohio, and U.S. Steel in Indiana. Each mill was also supplying battleship armor, destroyer hulls, and structural steel for Liberty ships. The WPB had to allocate their output by priority code. Sherman hulls were AA1, the highest rating, which meant they theoretically got first claim on production. But battleships were also AA1. And guess what? You can't tell the Navy their ships come second. Then there's the engine situation. Most Shermans use the Continental R975 radial aircraft engine, a 9-cylinder monster originally designed for trainers and light bombers. Continental's main factory in Muskegon, Michigan, could produce 800 engines monthly by late 1942, but Sherman production hit 200 tanks monthly that same year. The shortfall was covered by licensing the design to 6 other manufacturers: Chrysler, Lycoming, Gersonson, and others who had to be supplied with specialized aluminum alloys for the cylinder heads. That aluminum came from Alcoa plants in Tennessee and Washington, which were also feeding the B-17 and B-29 bomber programs. The War Production Board solved this nightmare through something called synchronized scheduling. Every Monday morning, representatives from the 7 Sherman contractors, their major suppliers, and the Railroad Coordination Office met in Washington to update a massive wall chart showing material flows. If Chrysler needed 500 engines delivered to Warren by Thursday, the chart showed Continental shipping 200 from Muskegon on Tuesday, with the remaining 300 coming from Lycoming in Pennsylvania on Wednesday. The railroads would allocate exactly the right number of flat cars to those routes, pulling them from civilian freight if necessary. This system had zero room for error. In March 1943, a rail bridge collapsed in Ohio, cutting the primary route from Carnegie Steel to the Pfizer tank arsenal. Within 6 hours, the WPB had rerouted 40 flat cars of armor plate through a southern route that added 200 Meller, but kept the delivery on schedule. The trains arrived at Grand Blanc 14 hours late, which meant Fisher's Tuesday morning shift started with a 14-hour material shortage. But the WPB had anticipated this and ordered Bethlehem Steel to ship an emergency consignment via express freight, which arrived Tuesday afternoon. Pfizer never stopped production. The scale of this choreography is hard to comprehend. By mid-1943, the 7 major Sherman factories were collectively receiving 22,000 tons of raw material per week via 1,400 separate rail shipments. The WPB tracked every single shipment in real time using telegraph updates from rail yards. So what did all of this actually accomplish? Between February 1942 and July 1945, American factories produced 49,234 Sherman tanks. 49,000. That's more than Germany's entire wartime production of all tank types combined. But the raw numbers only tell part of the story. It's the timing that mattered. By June 6, 1944, D-Day, Allied forces had enough Sherman stockpiled in England to equip entire armored divisions with backup vehicles already in reserve. When the 2nd Armored Division hit Omaha Beach, they landed with 186 Shermans and had another 40 in reserve ships offshore. When they lost 23 tanks in the first week of fighting, replacements arrived from depot stocks within 72 hours. This created a completely different kind of warfare than what the Germans were fighting. A Panther or Tiger tank was arguably superior to a Sherman in a one-on-one engagement. Better armor, better gun, better optics. But Germany produced roughly 6,000 Panthers and 300 Tigers during the entire war. When a Panther broke down or got knocked out, replacement parts took weeks to arrive, if they arrived at all. German tank crews in France were cannibalizing disabled vehicles just to keep their remaining tanks operational. Meanwhile, American armored divisions could afford to be aggressive because they knew losses would be replaced. They could send 5 Shermans to flank a single Panther, because even if they lost 2 in the process, 3 more would arrive next week. The 10-hour assembly time wasn't just about building tanks faster. It fundamentally changed military strategy. Generals could plan offensives knowing their armored strength would actually increase during the campaign, not decrease. The Third Army under Patton burned through Shermans at a ferocious rate during the drive across France in summer 1944, losing an average of 30 tanks per week to combat and mechanical breakdown. But the depots were delivering 45 per week, so Patton's effective armored strength grew even while taking casualties. That's a type of warfare Germany simply couldn't match. The production methods lived on long after the last Sherman rolled off the line in 1945. Japanese industrial observers toured American tank factories in 1950 as part of post-war reconstruction planning, and they were stunned by the modular assembly systems. Toyota engineer Taiichi Ono specifically studied the Chrysler tank arsenal's synchronized supply chains when developing what would become the Toyota production system and just-in-time manufacturing in the 1960s. The concept of breaking complex products into simple sub-assemblies using jigs to eliminate skilled labor and coordinating supplier deliveries to eliminate inventory. That's standard practice now in every modern factory, but it was revolutionary in 1942. Ford's jig and fixture library from Sherman production became the foundation for their post-war manufacturing renaissance. The same templates and quality control systems that produced turret components in 90 minutes were adapted for transmission housings, engine blocks, and chassis components in the 1949 Ford sedan. The modular design philosophy appeared in civilian products throughout the 1950s. Appliances, electronics, furniture, all benefiting from wartime engineering breakthroughs. The Sherman itself gets criticized by historians who focus on its armor and firepower deficiencies, but those critics miss the point entirely. The Sherman won because 49,234 of them showed up. The engineering triumph wasn't in the tank's design. It was in the system that could produce combat-ready armored vehicles faster than the enemy could destroy them. That's the real story of how engineers designed the Sherman to assemble in 10 hours instead of 300.